Today we're going to stick a parallel plate capacitor into a dielectric fluid. And we'll see it's actually drawn up into the capacitor to a certain extent. So we'll take a look at how that works. The capacitor equation is C equals Q over V. So the energy stored in a capacitor is 1/2 CV squared, or 1/2 Q squared over C. So if this distance is H, then the force drawing the dielectric up is going to be the negative change in energy per unit H. So we need to describe C in terms of H. And to do that, we'll also have to define a larger height. So for a parallel plate capacitor, the capacitance is just epsilon times the area over the distance between the plates. So we'll say the plates are some W wide, and then we'll have the capacitance of the area with the dielectric plus the capacitance of the area without. The capacitance of the area with the dielectric is going to be its dielectric constant, times H times W times epsilon naught over D. And this distance up here is big H minus little h, and the dielectric constant of air is essentially epsilon naught. So for the lower section, we have epsilon, K times epsilon naught, times the area, width times H, over D, plus the capacitance on top, epsilon naught, times the area, W times big H minus little h, over D. So dC dH is just going to be epsilon naught W over D times K minus 1. And that will be counteracted by the force of gravity pulling this back down. So we need to find the point where those two forces are equal. So the force of gravity is, of course, mg, which is rho times the volume, which is going to be W dH. And then solving for h, so once we start substituting in all the actual values for this experiment, in SI units, epsilon naught is going to be about 8.85 times 10 to the minus 12th. V is going to be about 2,500. K of 1.8. D of about 3 times 10 to the minus 3. Rho of about 800. And G of 9.81. All in all, this comes out to about 0.5 millimeter. But even 0.5 millimeter is noticeable when you see it. We can demonstrate this by pouring some dielectric fluid into this parallel plate capacitor and then charging it. Of course, it so happens that it requires very high voltages and a very good dielectric. So we're going to use some kerosene and charge it to about 1 kilovolt. Now your first instinct might be, won't the kerosene blow up? While kerosene is technically flammable, it has a pretty high flash point. It's relatively stable at room temperature. Here we have about 2 kilovolts. The kerosene has been drawn up into the gap between the electrodes. The effect is slight but noticeable.